We are going to learn about this concept called Wronskian. Now, why do we need Wronskian? Let's say you are given a set of solutions of a homogeneous differential equation. Now, if you want to know whether these solutions are linearly independent or not, Wronskian can do that very easily. Okay, so let's learn how. Now, what is a Wronskian? So let's think about a matrix. So instead of numbers in this matrix, let's say you have these solutions that are given to you arranged in a very specific way. Now the determinant of that matrix is what we call the Wronskian. So Wronskian is not the matrix but the determinant of that specially arranged matrix. Okay, so let's learn this arrangement first because that's crucial. Now I'm going to use the notation of the determinant because we are taking the determinant, and how many columns and how many rows you have, that is equal to the number of solutions that are given. So here, for example, in this case we are given two solutions, so we have two columns and two rows. Now the arrangement is, in the first row, in each column you put the functions that are given to you. So I put x here, I put 3x square here. Okay, now what about the second row? In the second row you put the first derivative of the function just above you. So derivative of x is 1, derivative of 3x square is 6x. Okay, now important thing, you cannot put 6x in the position here because 6x is the derivative of 3x square, so it should be below 3x square, right below it. That means in the position here, not in the position there. Okay, so you cannot switch the derivatives. All right, so let's do several examples. So here, two functions, so let's use determinant notation, two columns and two rows. So x and ex here. Now the derivative of x is 1, derivative of e to the x is e to the x. Very easy, right? Let's look at a 3 by 3 example. All right, so three functions, so three columns, three rows. So here x, ex, sin x. I put each function in a column. Now take the first derivative. That's the second row, right? Derivative of x is 1. Derivative of e to the x is e to the x. Derivative of sin x is cosine x. Now how about the third row? Guess it. That's the derivative of the first derivative of the row just above you. So that means derivative of 1 is 0. Derivative of e to the x is e to the x. Derivative of cosine x is negative sin x. Now you can think it in that way also, the first derivative of the row just above you. Or you can think this third row is actually the second derivative of the very first row, right? Second derivative of x is 0. If you differentiate e to the x twice, you get ax. If you differentiate sin x twice, you get negative sin x. So you can think it in either way, okay? Doesn't matter. Alright, so let me show you another way to do this. Okay, perhaps it will help you. Alright, so let's put each function in each column. Now you can complete column by column. So for example, first derivative of 3x cube is 3x square, and now take another derivative which will be 6x. First derivative of x to the 5 is 5x to the 4, another derivative is 20x cube. Now e to the 2x derivative is 2e to the 2x, another derivative is 4e to the 2x. You can do it in that way also, any method that you prefer. Okay, right, so that's just the special arrangement. Now how do you find the Wronskian? Super easy. Now you find the determinant of the arrangement that you just did. Okay, so we've learned how to find the determinant in the previous quiz, right? So here determinant is 6x times x is 6x square minus 1 times 3x square is 3x square. So what we get is 3x square. Now this is the Wronskian. So the determinant is 3x square. So Wronskian is 3x square. Okay. Alright. So that's what we call the Wronskian. Here let's take the determinant. So x times e to the x minus 1 times e to the x is e to the x. So if you simplify, we can take ex out. So then x minus 1. So this is the Wronskian. So I just factor ex out and this is what we get. So that's the Wronskian. Okay. All right. So I'm not going to find the Wronskian of these 3 by 3 matrices. You can do them by yourself as an exercise. We learn how to do that in previous quiz. Because I want to go to talk about linear independence, because we didn't discuss that, we just calculated Wronskian. Now how do you decide linear independence and dependence using that Wronskian? Here's the big theorem. Let's say you have given n number of solutions of a homogeneous differential equation on an interval I. Now you need an interval also, because when you talk about solutions, you have to give an interval, right? Where do they live? So we need an interval. So this solution set is said to be linearly independent on that interval I if your Wronskian happens to be not 0 for every x value in the interval. Now this is a very tricky statement, okay? So let's discuss this a little bit. So linear independence. So linear independent if the Wronskian is not 0 for every x in the interval. Okay, so what does that mean? Digest this very carefully. Okay, so Wronskian should not be 0 for everything. That means if you can at least find a 1x that makes Wronskian non-zero, then you are fine, right? Because what this linear independence condition says is, if your Wronskian happens to be 0 for no matter what x value in the interval, then you have linear dependence, or you don't have linear independence. So digest that very carefully. Okay, so what this simply means is, look at the Wronskian. If the Wronskian is not 0, if you can find a 1x value, at least a 1x value in the interval that is given, that makes Wronskian non-zero, then you have a linearly independent set. But if you can't find a x value that makes Wronskian non-zero, that means if the Wronskian is 0 for no matter what x value you have in the interval, then you have linear dependence. Okay, hope that makes sense. Okay, let's see an example. So here these two solutions, let's say they are solutions of a differential equation. Let's say the interval is from 0 to infinity. Good. Now what is the Wronskian? 3x square. So for example, when x is equal to 1, 3x square is 3, right? When x is equal to 1. So 1 is inside this interval. So is these two functions linearly independent? Yes, because one example is when x is equal to 1, Wronskian is not 0. So actually 3x square is not 0 for all the x values in the interval. Okay. Alright. So this set is linearly independent. Okay. Now you may ask, wait a minute, we have 0 here. Why didn't we talk about x equal to being 0? Because 0 is not inside the interval, because we have open brackets. Now let me put you in trouble by making it close bracket. Now x is equal to 0 is a point in the interval. It is included in the interval, not a point. Okay. Now when x is equal to 0, Wronskian is 0, right? So you may argue, well, Wronskian is 0 inside this interval. But not for every x value, right? You can still find a 1x value, for example 1 or 2, 3, 4. All the other x values doesn't make 3x square 0. It's just at one instant 3x square is 0 when x is equal to 0, but for all the others, Wronskian is not 0. So Wronskian is not 0 for every x. It's just 0 for one x. So it doesn't matter, right? Still linearly independent. Okay? Alright. So let's look at several other examples. So here, these two functions, these two solutions, x and ex, let's say they are two solutions. So in the interval 1 to infinity. So from interval 1 to infinity, this Wronskian ex times x minus 1, that's not 0, right? Because choose x to be 5. 5 minus 1 is 4. 4 times e to the 4 is not 0. So you at least have a 1x value. You can find many x values that makes this Wronskian non-zero. So this is linearly independent, these two solutions. Okay. Alright. So let me show you an example where it's linearly dependent. So look at these three functions, x, x square and 4x minus 3x square. Let's say those three are solutions of some kind of a differential equation, and in the interval is negative infinity to infinity. Now I find the Wronskian, which is a good exercise if you can do, and the Wronskian happens to simplify to 0. Now what does that mean? No matter what x value you use in that interval, the Wronskian is 0 because it is in fact explicitly 0, right? It is not even a function, Wronskian. We didn't get like 3x square or e to the x times x minus 1. We just got straight out 0 for Wronskian. So that means no matter what x value, this Wronskian is 0 for every x value in this interval, because it has nothing to do with x, right? So the Wronskian is 0 everywhere, right? So these three functions, are these three solutions, make a linearly dependent set. Okay, so that is how we use Wronskian to determine linear independence and linear dependent. Okay, so if you can arrange them correctly and if you find the determinant correctly, you can easily figure out the solutions are linearly independent or not. Okay, all right, so I will see you then in the next video. Thank you.